Majority of this video is going to be a bit different than my typical videos, which is why I'm shooting this intro video. I have created a research paper, which you can see in the link from the video, Beyond Tokens, Transforming Neural Networks into Adaptive Graph-Based Environment Reasoners. And then I fed this directly to an AI model, in this instance, Notebook LM. And then I created a podcast off of this, about a 26-minute podcast, where it dissects the paper quite in depth. I could recreate the podcast and take elements from it, etc. But I'd be creating a worse video overall. So I decided that the best way to present it would be to present the podcast overall and itself, and along with this intro. And then so in this intro, I want to highlight and point out two things before we get into the podcast. Very first one is that I do list ChatGPT 4.0 as a direct researcher on this paper, and that's not a gimmick. It's directly as a researcher on the paper. So to me, you look at the paper that introduced RLHF, put out by OpenAI in 2017, which very specifically lists ChatGPT 2 as a researcher on that paper. Same type of concept here, right? I wouldn't have developed AI geometry and this concept that we're going into here at all without ChatGPT 4.0. To me, it's just a formalization of the process that LLM models are doing anyway. Currently, right now, within our understanding, there's a gap between LM models as a token generator and a predictor of tokens and what they actually do, which is in instances they can translate languages, do soft reasoning, things like that. And then so within that, this paper is a formalization of that process of how does the LM model get from next token predictor to that. It creates systems within its own neural network and patterns within its own neural network, which create emergent structures. And then the model reads the patterns based off of that. I just create a formalization of that process that can be read then by other models and by humans, making this process more formalized overall. The second thing to note before we get into this overall is that there is one point in this where the AI model overall says that this is all theoretical, where that's not true. And I want to point out, so at the very end, I list here Appendix B of resources, and then the model doesn't have access to these links, right? It can't go through these links, but these are all actual tests. And then I go through, as the model is talking, you can see these tests going off. And then you'll see some of them, and then their actual benchmarks, etc. And then so this is a full end-to-end framework. I could build a full model off of this and train full models off of this. I've trained models independently and independent parts of this. I've built out the Lagrangian neural network, built off of AI geometry, as you see here, the Rhizome optimizer itself, as well as the topology-aware model trainer, which utilizes small LLM models and so pre-trained models overall. But highlighting that before we get into this, that this is not just a theoretical framework, that this is actually real world implemented, and you can see real world examples of it. So hope you like this and you like this type of content. Please like and subscribe. Thank you very much.
Hey everyone, ready to dive deep?
Always ready.
Okay, good, because today we're going way beyond the usual AI stuff.
Definitely.
We're talking about a research paper that's, well, it's pretty mind-blowing. It's called Beyond Tokens, Transforming Neural Networks into Adaptive Graph-Based Environment Reasoners.
It's a mouthful.
Yeah, but the ideas are even bigger. And one of the co-authors is actually a large language model, ChatGPT 4.0.
Which is, in itself, a pretty huge development. AI contributing to research at this level, that's new.
It is. But let's break down what this paper is actually saying. It starts with this idea that most AI today is really good at, and they call it token prediction.
Right, so think of it like, you have a sentence and the AI's just got to predict the next word. It's looking for patterns in the data it's trained on.
So kind of like our phone's autocomplete, but way more advanced.
Exactly. But here's the thing. That's not really understanding, not the way we do it. It's more like pattern matching, but very sophisticated.
So it's like that parrot mimicking words thing, but without really getting the meaning.
Exactly. And this paper argues that for AI to really get to the next level, it's got to move beyond just those tokens. It needs to understand how things connect, how the world actually works.
And that's where environment reasoning comes in. The AI needs to reason about its environment, like we do.
Right. And for that, it needs a way to represent what it knows, to organize all this information it's learning.
And here's where it gets really interesting. The paper suggests that the AI's neural network, it's like its own little universe. It's got its own model of the world inside.
It's fascinating, right?
Right.
Imagine that neural network as this huge network of points, like a giant map.
Okay, I'm picturing this map. What are these points? Like, what do they represent?
Each point, or node, as the paper calls them, it's a concept. So you might have a node for, let's say, dog, another for cat, another for walking. You get the idea.
And how does the AI know, like, how are those connected? How does it know a dog and a cat are both animals or that walking is an action?
Ah, that's where the edges come in. They're the connections between the nodes. So the edge might be dog to animal, showing that's a type of animal, or walking to dog, because, well, dogs walk.
And this network, this graph, it's growing all the time as the AI learns, right? New nodes, new connections.
Exactly. It's dynamic, always organizing itself. But what's really cool is the AI isn't just storing this stuff. It's actually using it to reason about the world.
So it's not just a database, it's more like, I don't know, a thinking machine.
Yeah, that's a great way to put it. And this leads into the paper's big idea, AI geometry.
AI geometry, that sounds straight out of science fiction.
It does, but it's actually pretty intuitive. Think about how Euclidean geometry, the basic stuff, helps us understand physical space points, lines, shapes. AI geometry, it aims to do the same for the AI's conceptual space.
Okay, I think I'm getting it. But like, what are the pieces of this AI geometry? What's the equivalent of points and lines in this concept world?
So the paper lays out four main parts. Nodes, the edges, structures, which are groups of these nodes that are related.
Like clusters.
Exactly. And
Wait.
transformations.
Wait, transformations? Like the AI can actually change its own knowledge map?
Exactly. Just like in regular geometry, you can rotate a shape or reflect it, and it's still the same shape, right? The AI can transform its knowledge structure to fit new information without losing what it already knows.
So it's not just learning facts. It's literally like changing how it understands things.
Exactly. It's always analyzing itself, seeing what works, what doesn't, and then making adjustments.
So it's like it's constantly editing its own tech book on how the world works. That's wild.
It is. And that constant restructuring is what allows it to really understand things at a deeper level than traditional AI.
Wow. But I gotta ask, how does this new geometry actually make the AI learn better? Like, what's the practical impact?
That's where topology-based backpropagation comes in. Basically, it's a fancy way of saying that it changes how the AI learns from the data it's given.
So instead of just tweaking a few settings, it's like the AI is actually rewiring its own brain to understand things better.
That's a good way to put it. So traditional methods, they focus on adjusting how strong the connection between nodes are. But topology-based backpropagation, this lets the AI change the whole structure of the graph.
So, like, it can literally restructure how it understands the world as it learns.
Exactly. It's pretty amazing.
Yeah.
And this ability to constantly change its knowledge map, that's what makes this approach so promising.
Okay, my mind is officially blown. So this AI's got its ever-changing knowledge graph, this map of how it sees the world. But the paper throws in another curveball. This AI's world is also a probability space, not just a map. What does that even mean?
That means the AI doesn't just work with things it knows for sure. It also works with uncertainty, like we do in the real world.
Right, because we rarely know anything for certain, so how does it handle that? The paper mentioned Gaussian and Monte Carlo something or other.
Yeah, those might sound intimidating, but they're just mathematical tools that help the AI deal with a world where things aren't always black and white.
So, like, could you give us a simplified version, maybe with a real-world example or something?
Sure. Let's say the AI is trying to predict the weather. It might have a node for temperature, another for humidity. Now, using a Gaussian distribution that's basically like a bell curve, it can figure out the most likely range of temperatures based on the data it's seen. But weather is complex, right? Lots of factors.
Right, it can't be that simple.
That's where Monte Carlo simulations come in. It's like running tons of virtual what-if experiments. What if there's more cloud cover or a cold front comes in? It runs all these mini simulations and sees how the results cluster.
So it's almost like it's playing out different possibilities, kind of like, I don't know, a chess player thinking a few moves ahead.
You got it. By combining what it knows about usual weather patterns with these probability simulations, it gets a much better prediction.
That's incredible. So this AI isn't just following rules, it's actually reasoning, dealing with uncertainty, and making decisions based on probabilities, kind of like how we think.
Precisely. It's that combination of the graph structure with the probability stuff that lets it reason at this level.
This is seriously mind-blowing stuff. And we've covered a lot already, but I feel like there's so much more to explore.
Oh, absolutely. We're just scratching the surface here.
Well, before we go any deeper, let's take a quick pause, make sure everyone's on the same page. This is some dense stuff. It's okay if your brain's doing backflips right now. We're all learning together.
Definitely. Take a moment, let these ideas settle in, and we'll pick up right where we left off in a bit.
All right, I think I've got my head back on straight. So, this AI builds its world, its knowledge map, this graph, but how does it actually improve it? The paper mentions topological optimization, and to be honest, that sounds kind of intimidating.
It sounds complex, yeah, but the idea is actually really elegant. Remember how we talked about the AI's neural network being this constantly evolving graph? Well, topological optimization is about finding the best possible structure for that graph so the AI can learn as effectively as possible.
Okay, so it's like the AI is constantly rearranging its furniture, but instead of furniture, it's rearranging concepts and relationships to make its thinking more efficient.
Yeah, exactly. Like you might move a couch to open up a room or add a bookshelf to organize your books. The AI uses topological optimization to make its thinking space better, more powerful.
But how does it know how to rearrange its furniture? Like, what guides those changes to its structure?
That's where it gets really interesting. The paper talks about an algorithm called the rhizome optimizer. You know how those underground plant stems spread out everywhere, forming a network?
Yeah, rhizomes. They're like the hidden brains of plants connecting everything.
Exactly. The rhizome optimizer takes inspiration from how those rhizomes grow, so the AI can adjust its graph structure in a similar way, dynamically.
So the AI's network is kind of growing like a rhizome, branching out, exploring new connections.
Precisely. And it lets the AI do some pretty amazing things. Like it can split a node into multiple nodes if a concept gets too complex.
So, say it's trying to understand renewable energy, it could split that into solar, wind, hydro, and so on to get more specific.
Exactly. Breaking things down into smaller chunks to understand the details better.
That makes sense. What else can this rhizome optimizer do?
Well, it can rewire edges, making the connections between concepts stronger or weaker, depending on how important those connections are for understanding things.
So it's always tweaking its understanding of how different ideas are related, like constantly adding notes to its mental map.
That's a great way to think about it. And it can also refine clusters, grouping related concepts together, and then rearranging those clusters as it learns more.
So it's like the AI is reorganizing its library, putting things in different categories to make better sense of the world.
Exactly. And this whole process, this dynamic self-organization, that's what allows it to reach that higher level of understanding we were talking about.
This is all so fascinating, but is this even doable with the tech we have now? Or is it more like a theoretical thing?
It's a good question. And to be honest, this paper is more about the theory than the specifics of how to build it. But they do point to some areas of research that could make this possible.
Like what? Give us some examples.
One thing they mention is developing specialized hardware that's designed to handle these complex graph calculations, like building a custom engine for a race car, something optimized for speed.
Instead of using general purpose computers, which are like all purpose vehicles, we could have specialized AI chips that are like supercharged engines built for this, right?
Exactly. And these chips could be built to handle not just the graph structure, but also the probability stuff we talked about earlier.
Wow, so we're talking about a whole new type of computing platform designed specifically for this new AI.
Yeah, that's the idea. And there are other exciting developments too, like new ways to represent knowledge within these graphs, making them more compact and efficient.
So like a streamlined language for the AI to think in, making it even faster and more powerful.
Exactly. It's about finding ways to optimize every aspect of this approach, from the hardware to the algorithms to how knowledge is stored.
This is seriously blowing my mind. But with all this potential, there have got to be some downsides, some challenges to consider, right?
Oh, absolutely. This is a really new field, and there are still lots of unanswered questions. One of the big ones is interpretability.
Like, can we understand what's going on inside the AI's mind? Can we follow its logic and see how it's making decisions?
Exactly. As these AI systems become more advanced, it can be hard to know how they're reaching their conclusions. It's an issue with traditional AI, but it's even more important here because everything's so complex.
So it's like building a super intelligent machine, but maybe not knowing how it thinks. That could be a bit unsettling.
It raises questions about transparency and accountability. We need ways to look inside the AI's black box, to understand its reasoning, even if it's operating at a level we don't immediately get.
That makes sense. We need to trust the AI's decisions, especially if they're going to be impacting our lives. What other challenges are there?
Another big one is data bias. AI is only as good as the data it learns from. If the data is biased, the AI will be too. And because this approach depends so much on the AI's ability to learn and adapt, it's even more important to make sure the data is fair, accurate, and represents the real world.
So it's not just how much data, but also the quality and the variety, right? Making sure the AI gets a balanced view of things.
Precisely. Otherwise, we could create AI that just reinforces existing problems.
That's a really important point. It seems like there's a big responsibility that comes with all this power, both for the researchers and for us as a society, as we figure out how to live with these super smart machines.
Absolutely. It's both an incredible opportunity and a huge challenge. We all need to be part of the conversation about how to use this for good and avoid the risks.
Well, that brings us to another key idea from the paper that I wanted to dive into: topology-based backpropagation. Honestly, even the name sounds like something out of a sci-fi movie.
It does sound pretty futuristic, right? But the idea itself is pretty straightforward. It builds on traditional backpropagation, which is how most neural networks learn.
Remind me how that works again. Something about adjusting the connections between neurons.
Yeah, it's like fine-tuning the network to get the output you want. But traditional backpropagation has a problem. It only focuses on those fine-tuning adjustments. It doesn't think about the whole structure of the network, that graph we were talking about.
So it's like trying to improve a car's performance just by tweaking the engine without considering things like aerodynamics or tires.
Yeah, exactly. And topology-based backpropagation is like taking a more holistic approach to car design. It brings AI geometry into the learning process, allowing the AI to adjust not just the small details, but the whole structure of its network.
So it's not just about tweaking numbers, it's about changing the whole structure of the network, like we talked about with the rhizome optimizer.
Exactly. It can split nodes, rewire edges, and refine clusters, all based on what helps it understand the data better.
So it's basically rewiring its own brain to learn more effectively.
You got it. It's a much more dynamic approach.
But how does the AI figure out which changes to make? Does it have an instruction manual for rewiring its brain?
Well, that's where topological gradients come in. They're like a guide for the AI's learning. They tell it how different structural changes would affect its ability to understand things.
So it's like the AI is always asking itself, if I change this, will it help me learn better?
Exactly. And by following these gradients, the AI can explore all the different ways it can structure its network, always trying to find the best way to understand the world.
This is seriously amazing stuff. So topology-based backpropagation lets the AI not just learn facts, but also change how it understands those facts. But does that actually make it better? Like, are there real benefits?
That's the big question, and it's early days, but the research suggests this could be huge.
How so? What kind of changes could we see?
One big thing is better generalization. Traditional AI often struggles to apply its knowledge to new situations.
So like a student who can ace a test, but then can't solve a real-world problem?
Exactly. But with topology-based backpropagation, the AI isn't just memorizing, it's developing a real understanding.
So it's like that student who not only learns the material, but also understands the ideas behind it so they can apply it to new situations?
Precisely. And that's crucial for AI that can actually work in the real world, where things are always changing.
That's a huge advantage. What else?
Well, it could also mean AI that's more adaptable and resilient. Because the AI is constantly adjusting its structure, it's less likely to get stuck or rely too much on old information.
So it's like the AI is constantly updating its map of the world, adapting to new things instead of holding on to outdated ideas?
You got it. And that adaptability is essential for AI that can function in a world that's constantly in flux.
That makes sense. Anything else?
One more interesting possibility is improved interpretability. Remember how we talked about understanding how the AI makes decisions? Well, this approach might actually make AI more transparent.
Really? I thought this was all about making it more complex. How could that make it easier to understand?
It seems counterintuitive, but by making the AI's structure more efficient, we might actually make its thinking easier to decipher. Imagine if your brain was super messy and disorganized. It'd be hard to find anything, right? But if your thoughts are organized, it's much easier to follow your logic.
So it's like cleaning up the AI's mental attic, making it easier to see what's going on in there?
Exactly. That could be a game changer for trust and accountability. If we can understand how the AI is making choices, we're more likely to accept its recommendations and use it responsibly.
That's a great point. It seems like this research is not just about AI being smarter, but also about making it more understandable and trustworthy. That's crucial if we want AI to be a real partner for humans.
Totally agree. And it brings us back to the core message. It's not just about building AI that can copy humans. It's about building AI that can help us do things we could never do on our own.
This has been an incredible journey so far.
There's still so much more to explore.
I'm ready for it. Okay, so we've covered how this AI builds its world, that graph, and how it's constantly tweaking it to learn better. But we touched on something even crazier before, the idea that this AI's world, it's also a probability space. What does that actually mean for how the AI thinks?
That's one of the things that makes this research so groundbreaking. Think about solving a jigsaw puzzle. You're not just randomly trying pieces, right? You use the shapes, the picture on the box, you're working with probabilities. Is this piece likely to fit here? What's the best next move? This AI, it kind of works the same way.
So instead of being rigid, it's built to handle uncertainty, to make the best guesses when it doesn't have all the info. Sounds a lot more like how we think.
Exactly. And it's all about combining that graph structure, which organizes its knowledge, with this probability space. That lets it deal with the fuzzy stuff.
We talked about Gaussian distributions and Monte Carlo simulations. How do those fit into this probability space thing?
Remember that weather prediction example? The AI might have learned that in, say, New York City, summer temps are usually in a certain range. That's where the Gaussian distribution comes in. It's like a bell curve showing the most likely temps based on past data. But weather's never that simple.
Right, tons of factors.
And that's where the Monte Carlo simulations are powerful. Imagine the AI running thousands of tiny what-if scenarios. More cloud cover. Cold front moves in. It runs all these mini simulations, each slightly different, and sees what happens.
So like it's playing out all the possibilities, kind of like a chess player.
Yeah.
Right? Thinking a few moves ahead.
Exactly. So it combines what it knows about typical weather with these simulations, and bam, a much better prediction.
That's wild. So it's not just memorizing, it's actually reasoning, dealing with uncertainty, making decisions based on what's most likely, like us.
Exactly. It's putting that graph structure together with the probability stuff. That's how it gets to that higher level of thinking.
Okay, this is seriously blowing my mind. And all of this ties back to AI geometry, right? This is the framework that makes it all possible.
Exactly. AI geometry, it's like the foundation, the language for the AI to build its understanding. Then those probabilistic tools give it the flexibility to work in the real world, where things are messy. Like AI geometry gives it the toolbox, and the probability tells it how to use the tools.
This whole deep dive has been incredible. My brain's still catching up, but this research feels like it could totally change the game for AI.
It really does. It's a big step towards AI that actually gets how the world works, interacts with it in a much more human way.
And it makes you think, like, if AI can learn to think this way, what problems could it solve? What could it discover?
The possibilities are endless, right? AI working with scientists to cure diseases, figuring out sustainable energy, maybe even exploring space in ways we haven't thought of yet.
It's mind-blowing to think about the impact this could have.
It's exciting to be alive right now, seeing this new era of AI unfold. And who knows, maybe someone listening to this will be the one to take this research even further, unlock even more possibilities.
Well, everyone, that's our deep dive for today. I don't know about you, but I'm buzzing with new ideas. This has really opened my eyes to what AI might be capable of, what the future could hold.
It's been great exploring this with you. The world of AI is changing fast, and it's through deep dives like this that we can keep up and get ready for what's coming next.
If you're as fascinated by this stuff as we are, check out the show notes. We've got links to the research paper and some other resources.
And remember, this journey of discovery, it never ends. There's always something new to learn, something new to figure out. Keep asking those questions, keep learning, keep pushing the boundaries.
This is The Deep Dive, signing off. Until next time, stay curious.